Hello everyone. I hope you're starting the week nice, and so I really hope that you're healthy, and focusing on the classes as much as you can. So this is our last full week. And next week, after this week, we will do Monday class, and Wednesday we'll take the last exam. Okay, so we have an exam in 1.5 weeks. So we did cover some of chapter 10, but now I really want you to focus on chapter 10 and 11 from now on. And we're not going to cover everything on chapter 11, but I'm going to give you some basics, and these two chapters are very important for future as well. Let's kind of go over chapter 10 review quickly. We start with making analogies between linear and rotational motion. And we basically just use different symbols, right? So we said that for distance or position, we had x in 1D. Now we have theta in angular, for angular position. And for the velocity, we had v in linear motion, and now we have omega. And if you think about the units, I'm gonna write those as well. So radians for theta, meters for x, and these are SI units. And for the angular velocity, we have radians per second, and linear velocity is meters per second. For the acceleration, we have angular acceleration as alpha, and that is radians per second square. In linear motion, we had meters per second square. And for the mass, we have kilograms, right? But for the I mean, this I is moment of inertia. It's not the internal energy. A moment of inertia, and since it is mr square, that's the form. So it has kilograms, but also r square, which is meter square. Okay, so you don't need to memorize this unit. You can just look at the equation sheet and see how what the form is. So this I here is in the form of mr square. Okay, and this is true if the mass is a point particle. So we're going to, we talked about this, but I'm going to remind you a couple things about that later. Next thing we did was, we did our mapping. We understand that it's nothing new. We just use kind of mostly the Greek symbols for angular motion, and we use the same descriptors. We use position, velocity, acceleration. That's how we started. And we looked at the units, we looked at the relations, right? And then we said that just like we did for constant linear acceleration, we can also apply the same thing for constant angular acceleration. Again, as long as the acceleration is constant. You have very similar equations to linear form. And we had those in the linear form as v is equal to v0 plus at was omega equals to omega 0 plus alpha t. And this is, I'm just writing in 1D, v0t plus 1/2 at. Of course, this is v0x, this is ax, right? But if you think about 1D, it's okay not to worry about too much about this labeling. But it is a good habit to kind of put those labeling correctly. I found my typo here. So this is t squared. Okay, so these are the two equations. We still apply step-by-step process, and that's what we did. We did go through some examples, some practice, so we use these. If you have any questions on these, please come to the Zoom meetings, and if it is Monday, Wednesday, Friday, just email us that you're coming. We'll be there. But Tuesday, Thursday, we do keep our meetings, so you can just pop in, okay? Next thing, so far we put everything separate. So we said like this is linear motion, this is rotational motion, but what is the relation between them? So then we related things. We start with from the arc length. So this was, you have an object maybe right here. This is the rotation axis with fixed point, and the object rotates, and this is r from the rotation axis to the point mass, and the object goes through kind of an arc, right? and this is going to be theta. If you don't say theta 0 is 0, then this has to be delta theta because it's the change in position, the displacement, right? And this was the arc length. So what we said then, arc length can be defined as this radius and the kind of the displacement, angular displacement, or theta. And we rewrote that as S equals to r theta, okay? And starting from there, so once you see this, and you can also check the units and everything. Since theta is radians, it has no dimension, and r is in meters, s is in meters, so meters equals to meters. That makes sense. So again, don't memorize this equation, just understand it, and it's in the equation sheet. And how do we get to the velocity from the position? Just like we did before, right? Since we are doing this since chapter 2, since almost the first day of the class. We took the derivative of both sides, and then the ds over dt becomes v. And r, since r is constant, the radius, r comes out of the derivative, and then this the first equation becomes d theta over dt, and that is the definition of omega. And then we got our velocity equation. We related linear to rotational using the velocity descriptor. Next thing is to get acceleration. How do we do that? Again, we take the derivative of both sides, and dv over dt is the acceleration. So in this case, kind of the you can see that the velocity is tangential, right? And if you have velocity in this form here, and you're taking derivative of that, you're going to get the tangential acceleration, right? So this is the tangential acceleration. That makes sense. You're getting this at from this above equation, velocity equation, okay? And right side, again, the r comes out from the derivative because it's constant, and d omega over dt, that's the change in velocity over time, but it's angular velocity, so it's going to give you angular acceleration as we have it in this equation here. Okay, so these are just to do the derivatives, right? And you will get those three one after another. And this radial acceleration is something that we've seen before. That's for the circular motion, uniform circular motion to be specific. And we said that this speed was constant. And are these the same speeds? This v in radial acceleration with the this v, are they the same? Yes, they are the same because they're both the tangential acceleration there, the tangential velocity there, okay? So v is again constant here. If v is constant, then we will think about what happens to acceleration, tangential acceleration. But if it was constant, then we said that this is uniform circular motion. But now we are looking at the cases that may not be the case, so it may not be uniform. Okay, so this may not be constant. It could be changing. So if you have a change, then you will have this tangential acceleration. Whether it's constant or not, you will still have radial acceleration as long as you have some speed. Okay, they come from the equations. So we know that the centripetal acceleration is given in this form. We derived that equation in chapter 4. So again, the t is for tangential, r is for radial, okay? And this r is, of course, pointing towards the center, right? Because this is a center-seeking acceleration. So this is the radial acceleration component. So you have the tangential one and the radial, and you can see that they are perpendicular to each other always. And since it's v squared over r, using the second definition we had in the second equation, v is equal to r omega, you can get the radial acceleration also in the form of r omega squared. But again, as I mentioned before, sometimes they're going to ask you to find acceleration. They're not going to specifically say tangential or radial. Then they mean it's the total acceleration. Since these two are perpendicular to each other, they're really asking you to find the hypo. Okay, so like this, let's use purple for the first time. This acceleration here in this case. These are kind of the components, right? And you can find out what that acceleration is. Since these two are perpendicular to each other, you just need to do Pythagorean theorem to find out. And then if they're asking for the angle as well, you can find it as just vector algebra. Okay, so that was the acceleration part, and we got these two, we got this equation from these two, okay? So next thing we discussed was the inertia, and this is moment of inertia, I, and it is found from the sum of point masses, right, at a distance r from the rotation axis, and has the mass m, and you just multiply those mr squares and then add them up because it's a sum, and that will give you the entire moment of inertia. Okay, so this is the way you do it if it is point mass, and then we talked about if it is a distributed mass, if you know the shape, if it's a known shape and you know the rotation axis it fits, or you can use parallel axis theorem, then you can just use table 10.2. I shared that handout before. I will do that again in this class as well, but there are known shapes and you can just simply use that if this equation not working, because this is for only for the point mass. Okay, so for some known mass distribution we can use table 10.2. If the distribution is more complex, that's probably not covered in this class, but I briefly showed you that you need to do an integral, and it will turn out later on, probably next year when you take math methods, you will talk about this, and it is going to be, you're going to see that moment of inertia is actually a tensor, not a scalar, not a vector, but a tensor. I'm not going to confuse you much about that. You will see that later on, and you'll do some calculations as well. So then we talked about the kinetic energy, and now we have two forms of kinetic energy. If the object is going through a translational motion or linear motion, then it will have kT. T stands for translational, and it is in the form of 1/2 mv squared. So whatever the mass of the object is, the linear velocity squared, and 1/2 of that gives you kinetic translational kinetic energy. And then we did talk about rotational. This is the case the object is rotating, and then we used the inertia I, right? So you need to look at what type of object you have, what is the inertia is. Again, you may need to use table 10.2 to figure out what the inertia is, and that goes in here, or you may need to do some calculations with using, if they are point masses, then maybe mr square calculations. And omega is the angular velocity. Again, there's a relation between v and omega. That's kind of how we derive this equation. I showed the derivation of this earlier last week. So again, remind yourself those. If it was not clear, please go back to those and quickly refresh. Later on, we will have both of these. So when we write our energy conservation, we are going to think about both of them if the object is having a combined motion. Okay, so it's both translational and rotational. But so far, we just have one or the other, not both of them at the same time. Okay, and we are going to discuss more of those. So we are going to start from chapter page 342, but I just want to highlight one thing. We have some good summary here, so I want you to really go through this before we start the next section. Especially these three are the new ones that we covered last time. So understand what a torque is, what math we use, extra math, the vector cross product, what is the right-hand rule. Please go through these before moving on. And in the next video, I'm going to start talking about the rotational form of the Newton's second law.